Okay, this is James Courson and his Artificial Intelligence CSC 480 Assignment 1 video. See here, this is the UI implemented to run the algorithms, and I'll just run a few of these. You can see that it's working. Solution path down here, length of solution, milliseconds, and space. Okay. You can select here between easy, medium, and hard. Notice the configuration is changing, and you can also input your own. Okay. So here's the code. This is my original servlet, which was the first page we saw that takes all the input. This one. This is the second servlet. Gets all the information. Here's the puzzle. Here we create the initial state from the data provided in the UI. This is our goal state, which we want to obtain. Here we create our agent, search the agent from the root for the goal using this particular search algorithm. All the rest just once we receive the solution, we populate all the information to display on the solution page. This one. So first we go into our agent. Where is he? Okay. Using the data provided from the UI, we retrieve our particular algorithm. We begin the search. And this is just details recording the information contained in the result. So our algorithm, go to search. This is the base class. Bunch of information storing. We have some abstract methods which are to be implemented in the specific algorithms. Base enqueue for a list of nodes. We leave the specific enqueue implementation to the particular algorithms. Dequeue just removes the first node off the queue. Check whether we are in a goal state. Does the current state match the goal state configuration? And then these are just getters and setters, basically incrementation methods for our data, our measurements. We have breadth first search here. For enqueuing, we just put on the end of the queue. All the searches, most of the searches start the same. You enqueue the initial state, start the time, execute the search, and then the real meat of each algorithm is in this execute search method. Check for the live state, record the depth. Here's the goal check. Here's the check for repeated states. If you are in a duplicate state, we will back up and continue executing the search from the next node, which, as you can see, first thing we do is dequeue a node. For the breadth first, here is duplicate state. Not really necessary for this guy. But for some of the others, we will check the history if the configuration has been searched. If not, put it into the map and return not duplicate, else return it is. Depth first. For this one, we have a special constructor for when we use the iterative deepening. Regular constructor. Here we enqueue the node at the beginning of the queue. Search is pretty much the same. Execute search. Most of this is the same. Here the duplicate state check comes into play. We check for the depth limit being reached, which doesn't really concern depth first search, but when iterative deepening calls it, we will use it there. Expand the node. If the expansion has contents, enqueue them. No contents and not the root, back up and execute search from the next queue removal. We're not really implementing these here either. Not necessary. Check for depth limit. This is also particular to iterative deepening, but it calls this, it creates this class, creates this object, so we put it here. Speaking of, we'll come here. Most of the same. Also enqueue here in the beginning, but we're doing depth first, so that's pretty much going to control it. Here we go, set initial depth. We loop through our depth first searches. This uses our special constructor setting the depth limit, which goes up to, I believe this is set for 40. When we get a solution, if we get one, record the information here. Again, not really using the heuristics yet. Greedy best first. Best. Okay, for this one, when we enqueue an object, or enqueue the node, first we'll set the evaluation function for the node. For greedy best first search, the evaluation function we use is the straight line distance along the array to the correct spot. So in this manner, we would have h of n is 0 if it's in the correct spot. We're calling our f of n, which is equal to h of n here. So we set that, queue the node, and then sort it and increase by increasing value. Again, search is the same. Execution, we have all of our checks. Expand the node. And then for A star is similar in that when we enqueue the node, we set the evaluation function, set the value. Here, depending on whether this is the alpha version or the beta version being the Manhattan distance version, we return our g of n plus h of n for the f of n. Here we have h of n alpha is the number of misplaced tiles. Beta, Manhattan distances. We do actually use our g of n here, which is the cost to get to the current node, which is recorded when we are creating our successor nodes. Our constructor here takes the type to differentiate between the Manhattan or the regular. And again, we come execute search. This duplicate state check is a little different than the others. Whereas this one, instead of checking for just whether the configuration has been reached before, it also checks the path to get to that configuration. And if the path is different, it will return it as a non-duplicate state. That's our Manhattan distance. This is when we backtrack up and prune. And I believe that covers all of the requirements for the video. Alright, so this is JBCourson. Let's see. Oh, I will show you the puzzle. This is the base class for the puzzle. It's basic information, getters, setters. We have two constructors. We can take the configuration as a string or a list of integers. I would just convert one to the other. The 8Puzzle itself is modeled as a list of integers. Stored also as string config, but that's really just to make it easy for me to translate back and forth. The 8Puzzle can generate its successors by taking a move. Actually, first down here it would generate the legal moves by finding the blank in the puzzle, and then using the blank to determine which moves are available to it. And this returns a list of available moves that we then use to generate the successor. All this is occurring in the node here. When we generate successors, generate your legal moves, and for each legal move, generate a successor. This is where we populate the node bookkeeping data. Come back here. When we take the move, generate a new puzzle using the current configuration and applying the move to it to determine what numbers need to be swapped. These are methods to find the blank, to determine that we use to determine what the moves are. And once a solution is found, we store it in the solution object, which is here, which is just some regular data holding this just holds the data, which is returned back to the servlet to be displayed onto the page. And there we have it. That is my implementation of the 8 puzzle solver.